Yeah, please allow me to introduce him quickly as well. All right, good morning, everyone. Welcome to the IEEE the Distinguished Lecture Program. The purpose of this program is to promote the field of electronic design automation to scientific community and the public at large. And today we are very honored to have Dr. Xiaoten Tan to join us. Dr. Tan is a professor in the Department of Electrical Engineering in University of California, Riverside. He received his bachelor and master degree from Fudan University and then PhD degree from University of Iowa. He also is a visiting professor of Kyoto University as an GSPS fellow since 2017. Well, as I'm presenting over here, today's talk is data-driven deep learning for full chip thermal and power estimation for commercial multi-core systems. And so Dr. Chan's research in recent years and focus on machine and deep learning for VSI systems modelings, thermal simulation, optimization, dynamic management, and so on and so forth. He published in more than 300 technical papers and co-authored 6 books. He also received many awards, and I like to highlight, for example, NSF Korea Award, and also best papers on major venues in the field like DAC. He also received the ASP-DAC Prolific Author Award in 2020. So there are more to talk about the Dr. Tan, but I wouldn't, consume too much time. So during the talk, and you can feel free to post and Q&A questions in the Q&A sections, and Dr. Tan will provide answers on site as well. Thank you. So it's all yours, and Xiaoten.
Yeah, Helen, thanks for the for this introductions. Yeah, I'm very happy to have this opportunity to present some of the research work, from my research lab. Anyway, I get this start, and then I will answer the question at the end of my presentations. Okay, thank you. Yeah. Hello, everyone. Welcome to my presentations. My name is Xiaoten Tan. I'm very honored to have this opportunity to introduce some of the research work done in my lab over the past 2 or 3 years. My presentation is titled Data-Driven Deep Learning for Full Chip Thermal and Power Estimation for Commercial Multi-Core Systems. Basically, I'm going to introduce some of the interesting research work using machine learning to predict thermal and power density map for the commercial multi-core microprocess. Okay. So as we know that machine learning pretty much is everywhere, have huge, profound impact on every aspect of our societies. I mean, here there's several areas we're familiar with. You can say recently the ChatGPT have really breakthroughs in the not just scientific community, right, in the whole societies. Okay, of course today we'll focus on the scientific computing EDAs, because there's also significant progress using machine learning to improve the efficiencies in many of the algorithms in the scientific computing areas. Of course, we focus on their application in the EDA areas, specifically how we can use machine learning to improve the simulation efficiencies. Okay. Now let's look at the high temperature issue facing today's high performance microprocess. As we know that high temperature can lead to severe reliability problems. But as today's chip dimension goes down, higher the temperature keep going up. The increasing power density and spatial power variation in the new generation high performance multi-core microprocess can introduce severe local hotspot problems. Look at this picture. This actually is the Intel quad-core i7-8650U CPUs. This CPU actually have 4 cores. Look at this floor plans. This right-hand side figure showed the thermal map captured by our thermal IR cameras, which indicate there's active hotspots running. That means that only one core actually is active. All other 3 core actually are idles. But this is not the good situation, because we expect that the task should run in the 4 core so that the temperature can be reduced and even distribute. So as a result, many thermal power regulation techniques have been introduced in the past, such as clock gating, power gating, dynamic voltage and frequency scaling, and task migrations. But one critical foundation for all this regulation algorithm actually is to correctly estimate 4 chip temperatures so that they can make the right decisions. But the problem is that it's very difficult to get those accurate thermal image map in the real time, because we cannot just use the IR thermal cameras to get those informations. So the problem is that how we can, accurately get this thermal image in the real times. So one may wonder, why don't we just use the on-chip sensor to get this temperature profile information? But unfortunately, on-chip temperature sensor cannot provide the full chip temperature information, because the number of the sensors typically put into the chip is limited due to the high design overhead. As a result, existing approach basically have to, based on the analysis approach, which need the accurate power trace of function unit as input. But often this power trace information actually is not trivial. Yeah. This picture shows quad core CPU. Actually, this is in one core where this is a sensor location and the temperatures, which is 82 degrees, and then this is a real hotspot. The temperature is 87. So you can see there first there's some distance between them. Second one, the temperature difference between them actually is quite significant. Yeah, it's like 5 degrees. So if we, based on the sensor information to make a decision on the thermal regulation, yeah, this may not be the best solutions. So existing approach to estimate the 4 chip temperature information is based on this Werner hotspot framework, where the input actually is the flow plan and plus the function unit power trace. And then they fit into this thermal circuit to obtain this temperature profile for all this function unit. But as we know that this is typically for the design time, yeah, they are not very efficient for the on-chip real-time estimations. Although there's a lot of existing approach, many numerical approach, but all of them are quite expensive. Yeah, not practical for the real-time estimations. This slide shows some of the recent work done in my research lab related to the thermal power aware online chip management and physical designs. Of course, we will not be able to cover all the topics today. So specifically, my talk will focus on 3 major areas. The first one focus on thermal hotspot and 4 chip thermal map estimations using machine learning based approach. The second one is that the 4 chip power density estimations also for commercial multi-core chips. The third one we focus on using convolutional graph neural network for fast thermal analysis for chiplet based designs. Okay. Here specifically, here's the outline of my talk. First, I would like to go through the background and motivation of this talk. And then I'm going to introduce the thermal IR camera setup system used in my lab to facilitate some of the research work here. Then I'm going to cover following specific topics. First, I'm going to show you how to do the hotspot heat source identifications. And then I will talk about how we're going to do the 4 chip thermal map estimations based on we call the high level utilization matrix using machine learning based approach. Okay. The machine learning based approach also will be show how to model this hotspot heat source of the multi-core chips. Then we're gonna show that how we're gonna use recently popular generative array networks to fast estimate for chip thermal maps using the supervised learning approach. Then I'm going to talk about how we're going to estimate for chip power densities based on the measured thermal maps using some of the analytical approach. Okay. Last one, we're going to show how we're going to do the fast thermal analysis based on recently convolutional graph neural network, especially for the chiplet-based designs. Okay. So now let's show that what's the difference between the proposed method and against the existing approach. As we know that existing approach basically is focused on the function unit power information. Those function unit power typically is obtained from some low-level proposed matrix using some regression measure to obtain. But this approach, some approach may not be very reliable. Yeah, most of approach is kind of like ad hoc, and also they need some flow map informations. So this is typically like hotspot based approach. Second method, as I mentioned, is based on the on-chip sensor, on-chip sensors. But as we know that typically you may not be able to put the sensor any location you want unless you can access the layout. So typically those kind of research is combined with the sensor placement algorithm together. Yeah, but as I mentioned, that this is probably is used for the design time based estimations. Also, the high overhead of the sensor may limit the number of sensors we can put on the chips. So then we may ask our question: do they have any other way, better way to estimate the full chip sense temperature information? Turns out that yes, especially for real-time applications. Yeah, turns out that there's many of real-time information about the chip utilization given specific workload. Yeah, we call it high-level performance matrix. Yeah, so if we know this kind of utilization information, and then we can use machine learning to generate these thermal maps. Yeah, this is actually what we try to achieve in our research work. So turns out that there's a number of research has been performed in the past to do the full chip thermal estimations. Yeah, so there's a we can classify existing amounts into several of categories. The first category is called a bottom-up approach. Basically, as the name suggests, that they try to build a thermal model from some of the existing numerical approach. For example, finite difference. This is actually represented by like hotspot-based approach. Then there's also a lot of research to develop so-called equivalent thermal RC networks. Yeah. So this kind of approach typically require it's more very expensive to compute because the network tend to be very large for very accurate thermal analysis. The second one is what we call top-down based behavior thermal models. Actually, my lab actually developed several of this approach. Basically, they try to build some of the system model using pole zero to capture the thermal response using the matrix pencil subspace identity method. Then regarding the power estimation, basically there's also a number of approach developed how to estimate the function unit based on some low-level performance count. Yeah, for example, this paper from our lab. Then there's some other approach. Basically, it's more of ad hoc. Yeah, so in general, estimate the function unit power is not trivial. So all the existing measures basically have some drawback. The first one is that they need to accurate power trace as input, but this is not easy to obtain. Second one is that the lack of efficient measure to map from the performance count utilizations to the thermal maps. Yeah, so in our work, we try to address both of the issues mentioned here. So as we know that one of the key difference between our approach and the existing approach is that instead of use the function unit power, we use a high-level performance matrix. For Intel chips, they indeed provide so-called Intel's performance counting monitor, IPCIs. Yeah, the table one actually indeed show the existing IPCIs from dual-core Intel process. Yeah, so you can say we do have a lot of global information. You know, this is for the whole chip. Then this is for specific core. Yeah. Then this is the second the thread. Yeah. So you can say for each core we do have a temperature information right here. Also have the chip frequency right here, and the construction count, and then the catch hit or catch miss. Yeah. For example, catch hit, catch miss. Yeah, for different kind of catch. Yeah. So they together provide all the utilization informations for a given specific workload. Yeah. And also we can access them in real time fashion. So it's very fast. So this graph shows the thermal modeling overflow by our proposed approach. Basically, we have this thermal camera system. We're going to talk about that later. And we using this thermal camera, we can record two kind of data. One is the thermal map information, you know, from here. And then at the same time, we can record synchronously all the performance matrix like IPCI, as I mentioned. And once we get all this data, and then we can use the machine learning to train the data using the performance matrix as the input, and then using the measured data from the thermal cameras as the output to train the networks. Yeah. So basically, this is the flow of proposed method. So to measure the on-chip temperature information of the thermal map, we call it, actually turns out to be challenging problems. The reason is that you know, first to really measure the temperature map, we have to remove the heat sink. Typically, if you remove the heat sink, the chip can burn out very quickly. So as a result, typically, traditionally, we have to provide some of the IR transport cooling to cool the surface of chip. But this cooling can cause the problem to the thermal imaging process because it can blur the thermal images. So as a result, you can say if you're doing that, this is left-hand side actually is the real thermal maps, yeah, here, and then the right-hand side actually is what you measure. So you can say they maybe can be quite different. So this figure shows the traditional way to capture the thermal image from the chip surface. Suppose that we have a chip like this, and it will put on the some of the substrate. And then to remove heat from the chip, right? Typically, we may have some liquid cooling flow from one side of the chip to another side to get rid of heat. And on top of that, you also need to add so-called air windows on top of that. And then you can use some IR cameras to capture the surface of the temperatures. So the problem is that actually we have 2 additional layers on top of the chips. So, and there's a lot of requirement for this flow, liquid, and air windows to make very accurate thermal images. So in this work, actually, we use totally different thermal image systems. So instead of we cool the chip on the surface, and then actually we cool the chip from the back. So this actually is the setup of the thermal imaging system. This is the thermal cameras, and then this is a chip. You can say between the thermal camera and the chip, there's nothing between them. So in this way, we can capture very accurate thermal images. And the cooling actually happens on the back side, and using so-called thermal electronic device, or called fan-tail device. And then below this fan-tail device, there's some liquid coolings, which is powered by some of the powers to get rid of the heat. Yeah. So specifically, we use this FLIR A325 SC cameras. Yeah, those are the performance characters of this thermal imaging cameras. And then in our examples, we use these two chips. This is a dual core process, and this is a quad core process. Yeah. Okay. So the first question we have is that instead of finding the temperature hotspot, actually we finding so-called heat source, the power density hotspot. So why a power density hotspot? The reason is that the temperature, the heat source hotspot actually is a potential temperature hotspot. Because in our work, we need to try to find all the potential temperature hotspot. As a result, it will be better off to find the power density hotspot. Yeah, we're going to explain this later more. To find the power density hotspot, heat source hotspot, basically we have to, get the power densities. So this is the general thermal diffusion equations. As we know, this is temperatures, this is heat source. Suppose that, we just look at the steady state. So we get rid of this transient terms. So this basically say that to compute the power density, right? And then once we know the temperatures, which can be measured by, thermal cameras, essentially, power density equal to the 2D Laplacian different comparison on the temperatures. Yeah. In other words, that negative spatial Laplacian of the temperature distribution will give you the spatial heat source. Yeah, heat source. Yeah. So you can say this is just one example. Suppose we have this 3 heat source, right? This is 3D information, and then if you compute temperatures, then this is the temperature you get. But if you take the spatial Laplacians, then you can get back to the power densities. Yeah, this proves that this method indeed work. So this figure give you some visualization how this the heat source hotspot is computed. Let's say we start with this temperature map, giving the left-hand side right here. So you can say the hot spot is pretty smooth in these regions. And then after 2D Laplacian transformations, then we get these fingers right here. You can say, well, we have a lot of heat source hotspot to this force. Yeah. So, but this just depends on specific workload we're getting based on this temperature maps. To find all the potential heat source hotspot, we have to run many benchmarks, maybe thousands of them. Yeah, to get all the completely list of the heat source hotspot. So this figure shows that if we perform the heat source identification method we just mentioned on all the benchmark we had using this 187,000 heat maps on this dual core Intel process, we get this heat map distributions, also called the local maximas. You can see they are, kind of distributed like this. So to be able to find the representative of this local maxima heat source, we use this k-mean based approach to cluster them into a few centroid, we call the centroid. So integrate this yellow dot. Yeah. So from now on, we refer this centroid as our representation of the heat source identified by our approach. Now we know that we can estimate a few power density hotspot using machine learning based approach. Next question we want to ask ourselves is that, can we estimate the full chip thermal map using some machine learning based approach? The answer turns out to be yes. Actually, we still want to use the utilization high level performance monitor, yeah, to as input of the systems. And then but the challenge here is that for thermal map hotspot estimation, we only need to output a few hotspot locations. But now the issue is that for a thermal map, we have to model every pixel of the images. Yeah, that can be a significant much more than we did. So the key issue is that can we still do this efficiently? Yeah. So this actually what we try to solve in this project. Here's the proposed the training phase and the inference phase for the proposed 4-chip thermal map modeling process. So basically, we introduce this DCT and IDCT image compression steps. When the IR camera get the thermal image, basically we first do the DCT-based image compressions, and then we only use this coefficient from this DCT process. And of course, we also get the performance matrix synchronously from IR cameras, and then we do the trainings, which will be similar to the previous hotspot estimation steps. In the inference steps, we introduce this IDCT process to recover back the thermal images. So in this way, we can dramatically reduce the computational cost and also the RN the size of the RN models. So this slide gives some information regarding the thermal image. So the raw thermal image actually have this size 177 by 166 pixels from thermal IR cameras, and then the number of pixels actually will be close to 29,000. Yeah, that's actually pretty huge. So as we mentioned, that the idea is that we use the DCT, 2D DCT, to compress the images into a few important coefficients. So in this way, we can dramatically reduce the number of output for our neural networks. Here just show some of the equation used for the 2D spatial DCT computations. Okay. So next question we need to answer is that how many coefficients we need for the image compressions. We did some studies. Actually, we use 140,000 heatmap images as the trainings, and compute the Roomy square of this image compressions versus number of DCT coefficient. As you can see from this figure, pretty much after like 36 coefficient, yeah, the Roomy square error does not goes down significantly. Yeah, so essentially we don't need to use more than 36 coefficient, yeah, for our image compression process. Yeah, so that's actually is the observation we have. So this figure shows some detail regarding the neural network architecture we used. We used the long short-term memory networks, LSTM. As we know that LSTM belong to so-called recurrent neural networks, which is very suitable for time series data. Because for thermal modeling, we may model the transient thermal map change over time. So LSTM actually is a suitable models for this modeling work. Specifically for our LSTM network, we have 5 hidden layers. 4 of them actually is using the hyperbolic tangent as activation functions, and 1 advanced layers which use the linear activation functions. During the training process, we have a 20% dropout to mitigate these overfitting problems. Also, we use OAT performance matrix from Intel as input, and then we have a 36 DCT coefficient as output. Here are some of the detail regarding the experiment setup. Basically, we have about 1 hour runtime data collect with the frequency of 60 Hertz. The benchmark we used have listed here. Some of them are process oriented, some of them are memory oriented, some of the system oriented. So in this way, we can including all kind of benchmark for our training process. For the LSTM, we basically have 100 epochs for the training with 60 time steps used in this training process. For all the data, 64% used for training, 16% used for the validation, and then the remaining 20% used for the testings. Yeah, we make sure that the testing don't have any overlap with the training date, so that we can really estimate the training errors. So in this slide, we show the comparison of 36 coefficient for the estimate the value and then the ground truth. You can say they all match very well for all 36. Of course, you know this one the more important, which is close to the DC values. Just like Fourier transformations, the date close to the DC is always more important than the date in the high frequency part. Yeah, but as we mentioned that the 36 coefficient will be sufficient enough to capture the whole information of the thermal maps. So after training is done, then the training model can be used to predict the runtime thermal maps. This tree graph basically just illustrate the measured thermal maps, the estimated thermal maps, and then the errors, yeah, the absolute errors. Of course, we also compute the root mean square errors for all the benchmark we are using. The average error about is 1.4 degrees. Yeah, this actually is pretty accurate already. Yeah, this slide just summarizes what we did for the 4-chip thermal map estimations. First, as we know that we have this thermal IR camera setup. So as we know that generative neural net become very popular for image generation. Among all this generative network, the generative adversary network, which is also called GAN, is the most popular one. So the GAN model basically consists of two components. The first one is called generators, and the second one is called the discriminators. The generator and the discriminator actually compete each other's. The generator will generate so-called a fake image, which fit into this discriminators, and then the real image will also fit into the discriminators. So the discriminator will try to distinguish between this real image and the fake image. It output a real or fake. The output will consist some the loss functions, which will feed back to the generator and then the discriminators during the training to improve the both networks. So basically, after training, we hope that the discriminator can distinguish the fake image versus the real image, so that it actually the net result is that it will generate a very realistic image, which is like the real fake image, which is like the real image. We also can view our 4-chip thermal map estimation process as image generation process. Among all the image generation neural network, the generative adversary network actually is the most popular ones. As we know that the GAN model has been used for the finger-to-finger transformation, trap-to-finger transformation, text-to-finger transformation, and sound-to-finger transformations. Yeah. So why don't we use the GAN model to transfer the performance matrix to the thermal image? Yeah, that's actually is what we plan to do for the our next project. This slide shows the proposed ThermGAN, which is a GAN-based 4-chip thermal map estimation method for multi-core commercial microprocess. As comparison, we also draw the traditional thermal estimation method. As you can see, the traditional method starts with the floor plan of the chip, and then the function unit power density information. They fit into some thermal models, and then eventually compute the 4-chip thermal models. Our proposed method, as we mentioned, start with the proposed matrix, which is a PCI data from Intel's, and then those information fit into the ThermGAN models, which will generate the thermal image after the trainings. Yeah. This slide basically give us more detail. Here's the ThermGAN architectures. ThermGAN is a GAN model. Basically, it consists of generators. The input of generator is the PCM data, which fed it into these generators. It first formed the fully connected layers, and then it upper sample to generate the fake image. Then either the real image or the fake image will feed into the discriminators. The discriminator actually is normal convolution neural network. It will first create this the image, and then it will downsample into the potent features and create this fully connected layers, and then the PCM data also concatenated with this fully connected layers here, eventually to form the two fully connected layers. The output will be just one values indicate if the image is real or fake. Also, the loss function will be formed to train both generators through this feedback loops, and then the discriminators. Yeah, here's just some hyperparameter used for our ThermGAN models. So this graph gives a further illustration of both generator and the discriminator used for our ThermGAN modeling. So basically, the PCM data will form a fully connected layer, which including 170 number of the cells, and then it will generate another fully connected layers. So this fully connected layer will receiving into this the tensors. So through this upper sampling process, we're going to create the thermal maps. Yeah, this actually is a fake image. Then the discriminator basically take input as a thermal image, which can be real thermal map or the fake thermal map, thermal image, and then it will downsampling to generate this potent features and form this fully connected layers, which concatenated with the PCM data to form this another two fully connected layers. So this discriminator will eventually judge if the input is fake or real one. We use 25% of the samples for the testing, and then the remaining 75% for the trainings. Among the 64,000 test set, we found that the average error is about 4.7 degrees, with a standard deviation of 0.56 degrees. That means that the mean square error actually belongs to 1 degree. Yeah, that's actually very accurate. Yeah. Also, we use about 10 epoch for the trainings. Yeah, this graph just showed that how the thermal map gonna change over time compared to the ground truth. Regarding the time, we found out that the average cost for the inference is about 7 milliseconds. Yeah, that's actually translated that we can get about 140 thermal map per second. Yeah, that's actually sufficient enough to for the online thermal and power regulations. So this slide shows the accuracy comparison with another two methods. The first method is based on the long short-term memories, as we mentioned previously. So in this case, we'll compare two methods in this Intel quad-core process. The second method is called the heatmap. Heatmap actually is called a per silicon thermal estimation method, because this method requires optimum sensor placement to achieve the best result. Also, this method needs to per calculate and save this matrix in the memory, which is huge, 3.2 gigabyte. As a result, this two methods actually is now real apple-to-apple comparisons, but we just compare the accuracy between these three methods. So this table just shows that in terms of accuracy, ThermGAN beat both methods, yeah, in terms of mean error and the standard deviations. Also, in terms of inference speed, the ThermGAN model also is fast than the LSTM method. So this graph further shows the real-time capability of ThermGANs. We run ThermGAN brand new workload, which it have never seen. Basically, we run ThermGAN on the CPU for 2 minutes, and then collect 7,000 samples. So we found that ThermGAN actually yield the average room mean square error of 0.87 degrees with the standard deviation of 0.50 degrees. Yeah, this actually is very accurate, consistent with our previous observations. Then this cartoon illustration showed the estimate the thermal map real time and then the ground truth. As you can see, they match very well, almost in the real time. To further illustrate of the accuracies, we actually collect the thermal information at one particular location on the chip, and then plot this thermal information over time. As we can see that the blue lines are ground truth, and then the dotted line is estimate. As we can see that they match very well, pretty much all the time period. Now let's switch to the third topics. Here, the problem is that how we're gonna try to estimate full-chip power density maps, giving the thermal maps. Suppose we can have a measurement from the thermal maps. Yeah, let's go quick. Here, I'm gonna show the specific problem we try to solve. Suppose we have this thermal maps from the measurement of some computation softwares. The goal here is that how to estimate power densities, full-chip power densities. Here, you can see that this actually is the kind of like reversed problem from the power to thermal. Here we have from thermal to powers. Yeah, so there's many existing approach in the past, and many of the existing approach actually is defined as a regression and the optimization problems. Yeah, which tend to be very expensive. Also, as I mentioned, some problem I should combine the sensor placement with this power density estimation problems, but they are no longer post-silicon based approach. Okay. Now let's look at how we're gonna fund this 2D thermal density maps. We start with this thermal equation in 3D form. Here's because here we talk about steady state temperatures. We can remove these transient terms, okay? As a result, we end up with this equation. This equation basically says that the power densities in 3D, yeah, of course, we only focus on the XY, we are interested in this XY surface, equal to this equation. This actually is the 2D temperature Laplacians, negative 2D Laplacians, times this kappa, which is thermal coefficient. Then, of course, you know, sounds like this is very simple, but turns out it is not, because there's two issues. First is that how to estimate the kappa, yeah, which because the temperature the power density here you get is scaled power density, not a real one. Second one is that we observe that in addition to the power, there's a positive power density, but there's negative power density. Okay, yeah. This actually is true across all the thermal map we opted. Yeah. So result, we have to figure out how we're gonna using this so-called raw power density map to estimate the real power density maps. Yeah, this is the problem we try to solve. Okay. Here actually is the framework to guide our research work, how to estimate real power densities. Basically, we start with some ideal case. I'm going to talk about a little bit later. Here, we know exactly what the power density will be. And then we run through this thermal models, get the thermal maps. At the same time, of course, we know the total powers. After that, we use our proposed method to estimate the power densities from these thermal maps. Then we're going to compare with this ideal power case to say if they agree. If they agree, and then we know how we're going to compute the real power density maps from this measured thermal maps. Yeah, so this actually is the workflows. Okay. Here we talk about we actually have two cases. Yeah, the first case actually is the very simple case where you have uniform, homogeneous heat source in these squares. Of course, this is another board, set up this kind of environment. The heat actually flow downward in these directions. Okay. Then based on some of the thermal models of these structures, we can, using console, we can compute this thermal maps, okay, 2D thermal maps. After we get these thermal maps, we do this 2D Laplacians, and then we get this power density map. From this power density map, we can see actually is that indeed we see there's a positive part right here, the yellow and these colors. And then there's negative power densities, which is the old green part, blue part. I'm sorry. So as we know that the real power actually is in this region, not in this blue regions. This just represent the power dissipations, but power generations actually is constant in these areas. Okay. Yeah. So actually, we found that if you do this integration of power density all across the whole chips, every pixels, you will find that the positive portion and the negative portion actually if you add them together, will be zeros. Yeah, this is actually not a surprise because we talk about the steady state. Yeah, the net power density must be zeros. Yeah, must be zeros. So so that's actually confirmed that our observation that you have a power generation, then you have a power dissipation. They actually equal to cancel each others. Here is some of the formulas we have. Basically, we say that this 3D volumic power density, right, can be equal to this Pxy, which define the surface power densities. And then this Pd represent the positive, the dissipation power density, but they are also surface. And this is a chip thickness, delta Z. So this volumic power density will equal to these two surface density difference divided by delta Z's. Okay. And then we can replace this power density by that thermal equations right here. If we do this integration across all chips, we end up with this these formulas. And then after that, we end up with these formulas. As we know that eventually this integration will lead to zeros. That means that the P equal to PD, right? P equal to PDs. Okay. Then inspired by this ideal case, as we show these two ideal case, we can, one simple idea actually is that we just consider only the positive portion of the raw power maps, without consider all the negative part, because as two cases demonstrate, right, the real power is concentrated in these positive portions. So as a result, we just consider this this region we call indicated by this SP, which approximate to the power. This is divided by delta Z, yeah, because we know this total power, right? And from here, basically, we can estimate the power, the coefficient of kappas, yeah, kappas here, okay? Then if we move this delta Z to the left-hand side, then we can estimate this K times delta Z using these expressions, okay? So as a result, the actual 2D power density map can be estimated using this approximate formulas. Basically, we say that if the power density is positive, okay, then we're using this expression. This K delta Z is computed by these expressions, yeah, based on this positive part. Otherwise, the power density will be zeros. Okay, at least we can say this is a valid assumptions for this two ideal case, the uniform case and these linear forms. But even for these two cases, we found that the similarity is not 100%; it's 96% accurate. Yeah, but the room square error is pretty small. Yeah, pretty small. Okay. Here we talk about the experiment result we have. First, we showed that for the K, right, which is estimated thermal coefficient, they are pretty stable across different time. Of course, you say there's some spike in between. This basically is come from the transient behavior, because we talk about steady state, but indeed, our measured data have some transient data. So as a result, we have this kind of spike. Okay, but general, we found that this is pretty stable numbers estimate based on the data we have. This experiment also showed that for this i7 quad-core process, which have this is this Intel i7 quad-core layout. Okay, and then this is actually is the estimate power maps. Yeah, and then this we just overlap these two fingers. I have this one. You can see the hotspot actually indeed happened across this CPU cores. Yeah, and so this is indeed validate our estimation approach. Okay. Here we go further. Based on the estimated thermal power, we actually use console to build the FEE finite element thermal models. Because here we try to using this thermal model to map this estimated thermal power back to the temperature again, and then we can measure the temperature against the measured temperatures. Yeah, because this is the ultimate kind of comparisons against our proposed approach. Of course, we try to mimic the real chip setup, based on this kind of information we have. And then, of course, we also measure the CPU die, so that we know where's the boundary conditions. Yeah, okay. Here's the result. The first line actually is the real experiment result measurement, from our IR thermal image system. Okay, and then the second row actually showed that, of course, for different workload. Also, this second row showed that for different workload, right, this is estimate power density maps. Look at here's, look at here's, and then the last row showed that using this power density and then the finite element thermal models, this is resulting estimate thermal maps. Okay, thermal maps. From here to here, you can see this estimated thermal map actually matching the measurement very well. Very well. Yeah. So we found that the largest error, room mean square error, is 1.8 degrees. Yeah, over this 60 degree dynamics range. Yeah, we consider this is a pretty accurate, very accurate already. Yeah. Here's the last topic I'm going to present today. How we're going to perform fast thermal analysis for chiplet-based designs. So as we know that chiplet-based design become very popular recently because it provides many benefits compared to existing single die-based designs. For chiplet-based design, actually one of the major concern is that because you have to integrate many chiplet together, the thermal aspect of the chip design actually is a major concern. For instance, during the placement of different chiplet, right, we have to estimate the thermal impact. So as a result, fast estimation of thermal impact for different flow plan of the chiplet placement and flow planning actually become very important topics. Yeah. So today we're going to show how we can perform such fast thermal analysis. Okay. Actually, there's many approach has been proposed for some. So how to deal with these issues, as we know, how to generate model which is more have more transferable analogies, can deal with different problem size. Basically, there's two approach to deal with this problem. One idea is that using this tile-based method. Yeah. So basically, they partition the whole chip into a different tile, and then they perform this machining on each of these tiles, and then after that, they put all these tiles together to build the final solutions. Because we just focus on local tiles, so even we can deal with different the problems because the problem may have a global. They are different globally, but locally they may be same. Okay, so that's basically assumption of this tile-based approach. The second one using so-called graph convolution networks, because graph neural network by nature actually can deal with a different problem, because the input of this graph neural network is a graph. Yeah, graph can be a different graph. Yeah, which means different problems. So naturally, they can deal with different problems, even they are trained on the linear side of data. Yeah. Okay. Now let's look at the traditional numerical-based approach. As we know that the traditional numerical-based approach, like finite element or finite difference-based approach, they actually first converting this problem into some kind of graph using this discretization-based approach. Okay, so as a result, they already convert the problem into graph. So actually, we can leverage existing numerical-based approach by using the graph they generate. Yeah, specifically in our problem, we try to use this finite difference-based approach based on the hotspot. As we know, they actually convert this the problem into some kind of the resistor network or resistor capacitor networks. Okay, as shown here. Specifically, though, let's say we have this sum of resistor networks, which is converted using the hotspot. Okay, and then after that, we're gonna define this graph. Okay, the graph actually is an undirected graph, and with node and edge, as we know, right? So the node are gonna embedding some feature, for example, power, temperatures, and the edge are gonna embedding information like resistors. In this case, sum of resistors. Okay, yeah. As a result, we end up with this kind of the summer graph. Let's put that way. Here, I talk about several existing techniques proposed for the graph convolution networks. The basic idea of the graph convolution network is that we try to computing this this graph information for each node based on this neighborhood informations. Yeah, so this is called convolution operations. You know, so the way to do this convolution operations, there's many methods to do that. Okay, so the first idea we try to borrow actually is that so-called graph attention networks. The idea actually is that we're using this called attention coefficient to consider this connection effect, connection effect. So here essentially is a sum of resistor effect. Okay, this is first ideas we the second idea we borrow actually is so-called principal neighborhood aggregations. Okay, so the idea is that instead of using one aggregators, we may use several of them. For example, we use mean, variation, maximum, minimum, so on and so forth, instead of just using one. This graph just showed that if we just using one aggregators, we may not be able to distinguish this graph. For example, 2, 2, right? 0, 4, right? Average always 2, yeah. So we cannot distinguish this graph. This is also true if we just use the aggregator show up here in these oranges, yeah. So if we use all of them, then we can distinguish all this graph. Okay. The third idea actually is that we use this so-called escape connection. Yeah, we using this concatenation ideas. So idea is that we may connect the different layer directly. Using this escape connections. Yeah. After that, we're using this concatenation operations to connect this two sensors into the large sensors. Yeah. Some of the sensors maybe come from direct connections. Okay. So based on the idea we just discussed, then we end up with the proposed convolutional graph network architectures for the thermal analysis for chiplet design. So for this architecture, you can see we have a total power, then we have a power for each of the nodes, and then we have a sum of resistors between different nodes. Then we have this attention networks to consider this sum of resistors, and then we have this aggregations to increase the modeling capabilities. So after all this operation, and then we can output the temperatures for each node. Okay, Here, mathematically, we can represent this operations here. This represent the escape connections. This represent this PMA aggregations, and then this represent this attention networks. Okay. Here, give one examples. In this particular examples, we have 4 nodes, 5 nodes. This node connect to 4 nodes, and then there will 4 edge connect those 5 nodes. Okay. This is resulting the CNG graph networks. So basically, here, this attention network is actually consider all these reducers. And then here's the aggregations, consider different kind of values. And then here's the skip network, consider the total powers, okay? And this part actually can update this age features based on the node informations, okay? So basically, here we want to summarize the feature of the proposed networks. Basically, we use global information total power as input. We actually apply these skip connections in the graph network to consider this global informations. We integrate this principal neighborhood aggregate networks into our models, and we use age-based attention network to represent the connections between different nodes. Okay. Here we talk about how we're going to prepare our date. So as you can see, each node actually have a node ID power, of course, total power, and the age, of course, represent the sum of reducers. The output actually mainly represent the temperatures, temperatures. Okay. So for our problem, okay. So basically, we consider heat sink, heat spreader, and the chiplet. Okay. Yeah. This of course is a little bit more simplified modeling of this thermal analysis. So when with 60 by 60 by 3 reducer networks, this is the number of nodes we generate. It's a pretty still pretty large networks. Okay. Now let's bring some of the results. So first thing we do is that we try to generate the testing set. For this purpose, actually, we randomly generate the position of the chiplet. Here is the examples. Yeah. So we generate about 8,000 samples, and then 85% used for the training and 50% used for testing. Okay. So here's the result. First, we don't consider this aggregation features because it's more fast in this way, and compare with the hotspot as ground truth. So you can see this is a thermal image at the chiplet level, high spread level, and heatsink levels. Yeah. So as you can see that relative error is about 0.91%, and the mean root mean square is about 0.35 Kelvin, and the maximum absolute error is about 2.5 Kelvins. Okay, this actually is not bad. Then we add this PNA. Yeah. So so as a result, you can see the relative error, root mean square, and maximum absolute error all reduced. Okay, all reduced. This graph shows that the predict temperature and the ground truth, how they correlate. Yeah, they actually correlate very well. Yeah. The second example we try to carry out is that instead of using the during the training, of course, we're using this 4 chiplet. After that, we're using more different number of the chiplet on same layout. Okay, see what happens. Yeah, for example, this is hotspot ground truth, and this is the GCN plus the aggregation operations, and this only use the GCN without aggregations. So from here, we can see that the result in terms of error actually is pretty good. Yeah. So maximum error is just 1.8 Kelvins. Yeah. So maximum root mean square is at least 1%. Okay. Then we further test our proposed simulation method. In this case, the chiplet actually have different size. Okay, chiplet, although they are still full. Okay, and then we'll test how it compared to the ground truth. So here's the, of course, we in this case we also distinguish two cases, the GCN with the aggregation operation without aggregations. So we can see. So in general, with the aggregation, always lead to the less errors compared to without the aggregations. Okay, yeah. This graph further show that let's say we use the different chip size. You know, for example, 12 by 12, 15 by 15, 18 by 18. Okay, and then so how our measure gonna fare in this case? So from here you can see that. The GCN plus the aggregation operation compared to the ground truth, they actually are pretty close. This 18 by 18 seems a little bit more visible errors, but in general, you know, the difference is not very significant. This graph gives a little bit more detailed information in terms of all these comparisons. So, but in general, using the GCN models, which can achieve about 4.8% speed up over the hotspot, yeah, using SuperU. If we add this aggregation operation, then the speed up over hotspot is reduced a little bit. Yeah. Actually, I want to mention that. From speed up perspective, we found that the graph-based network is not very significant, you know, compared to the traditional hotspot. Yeah, this actually is one of the major drawback of graph neural network because there's you know no reduction in terms of graph during this modeling process. So if you have a big graph, then you have more computations. Yeah, this actually is a little bit different than the image-based, let's say, game-based approach. Yeah, they are a little bit more scalable for different purposes. But for graph neural network, we found that scalability seems not as good as the traditional image-based neural networks. But the benefit actually is that they are more flexible, powerful to deal with different city problems, as we demonstrate here. Okay, yeah. So before I finish, I would like to thank my current student, Jingwei Zhang, Wentian Jin, and my postdoc, Dr. Liang Chen, and my former student, Sheriff Sadabatra, for their hard works, so that I have the luxuries to present today. I also like to thank my collaborator, Professor Hossein Amarach from University of Stuttgart, and Professor John Hanker from Karlsruhe Institute of Technologies, for their collaborations, especially for setting up the thermal imaging systems. Of course, you know, I would like to thank all funding agencies and natural science foundations, which provide all the major fundings for the work I present here today. Thank you. Oops. Oh.
Thanks, Sheldon. Thank you for very inspiring and informative talk. And I mean, your group has done a lot of work in this domain. I saw there are some questions in the Q&A session.
Okay.
Yeah, go ahead. Yes.
Yeah, the first one, of course, we have a recording, yeah, as we know. It's IR's transparent cooling unit benchmarking against the original heat sink to validate the difference. Yeah, this for this question, actually, we actually have this, you know, the camera manufacturers come to our lab, you know, to do some kind of collaborations every 2 years. Yeah. So I believe that during this process, they collaborate our camera system with the real source. Yeah. So actually, we also upgrade our lens, yeah, recently to double the resolutions, so we can get a much better, you know, better image systems. So, okay.
Any other questions from the audience? I do have a quick question, Shelton, since everyone right now is talking about the AI and the machine learning methodology, and
Right.
then people also talk about the importance of the data and the volume of data. So for your research, and do you see any challenges in getting qualified data, and how do you address this?
Yeah, this is a very good question. Yeah, I think data is the most important thing, as we know, doing the machine learning. For our program, yeah, you can say, fortunately, we have this thermal-aware camera, right? They provide much realistic data than the traditional simulation-based data, right, like hotspot. So this actually provides huge kind of convenience for us to collaborate our data with a realistic situation, right, like commercial. Commercial chips. Yeah, we talk about here, right? Versus a lot of research work in the past, right? They pretty much based on the simulation-based data, and then they do this machine learning. But here you can say a lot of our data actually come measurement, yeah, on measurement. So that's actually provide a very solid foundation to calibrate our approach. Yeah, I want to mention that. Our proposed approach actually is I believe the first time we actually can really do the real-time thermal estimation based on the commercial chip. Yeah, we actually work on the Intel chip right now. Recently, we also published one paper talk about use for the TPU, Google TPU. Yeah, how we're going to do the thermal model for the first time. Yeah, for TPU even difficult because TPU don't have that. Benchmark, high level benchmark, the utilization benchmark. Yeah, somehow we manage this to get the thermal map. Also, our lab is working on the AMD chips. Yeah, we found that AMD use a little bit different utilization matrix than Intel's. So hopefully we can still validate our approach on AMD chips. So in that way, we can pretty much cover most of the commercial microprocess. Yeah, using our approach. Yeah.
I see. Fantastic. Actually, there's a follow-up question. So excellent section, sir. Any online free tools for power analysis?
Good question. I think we already published this triplet, the code in the GitHub. Triplet already published. And for the other tool, we can publish. Actually, from network perspective, it's pretty simple, right? We use the long-term, short-term memories. Yeah, it's just like the setup, the whole thing is pretty complicated. But we definitely publish. Yeah, if you guys want to know, I can follow up with the link. Yeah, for that chiplet design, we already published that. Yeah, in the GitHub. And we already get a lot of download already.
Well, yeah, thank you. I guess in Shelton, we can share more such information to society, and then people can test your tools as well. Okay, so it seems like we ran out of time today.